Sometimes when I watch TV or when I watch YouTube, I suppose, or when I'm just out and about in a social place, and you hear people discuss whatever, right? And then sometimes I hear people say this. Oh, what you say makes no logical sense, or by what logic does that make sense? And I always think to myself, do you know how to check if something makes logical sense? Hello everyone. So if you watch the prologue videos, then you should be ready to learn maybe something more advanced. Like I said before, the prologue was just to put everyone in the same level, even if you are not a math major, right? Now, in my very first video, I said that I want to show people what math majors do. Like maybe if you're thinking of, you don't know what you're gonna do in college, you don't know which major to choose, and you might be thinking, oh, maybe I want to do math, right? Well, I wanna move into that territory, and before we can do that, we need to talk about how to prove statements. Now, I've done some proofs already, right? And some proofs I didn't do. I said, I owe you. I'll do them later. Well, most of the proofs that I did, you could call them direct proofs. Starting point to finish point, you can get there pretty easily. And I think the ones that I said I owe you for the future, well, some of them was maybe not necessarily that you can't really prove them directly, but rather that it's easier to prove them indirectly. Now, what does that mean? Prove something indirectly? Well, we math people are tricky people. We figure out a way to say what you tell us. You know, with completely different words, but with the same logical meaning, and that usually makes our work a lot easier. Well, what does that mean? Two sentences being structured differently but meaning the same. Or rather, not just that, but having the same logical meaning, right? What does that mean? Well, it might be, I think it's actually hard to describe, but easy to show. And the way we show that two things are logically equivalent, well, one quick way to do that is to use truth tables. Yeah, I mean, as you can already kind of tell, math people figure out how to do math with logic. You know, of course. Yeah, math logic or logic math. I don't know, something like that. I know, sounds horrible either way, right? But you'll see that maybe it's actually a lot simpler than you might think. Um, it only depends how complicated you want a statement to be, or how complicated you want to make the statement. But yeah, again, this is a necessary discussion because not everything it can be. Well, I mean, not everything is easily proven, directly from point A to point B. Sometimes we gotta take some detours. Uh, you know, Sometimes you just figure out that there's different ways to prove something, more creative ways, which maybe give you a better insight of why something might be true, right? So again, math majors, all they do is prove things. Then we don't really calculate that much thing. Not after calculus, right? So if we're gonna prove things, it's better that we have a whole repertoire, a big arsenal of different ways to prove a statement. So before I can actually get to the nitty gritty of what math majors do, we need to talk about what are ways to what are the different ways of proving mathematical statements. Okay, so logic, right? I guess that's the title for today. Logic sounds kind of funny, right? Um, so what's the deal, right? So what I've been saying is that mathematicians, we don't really calculate stuff. I mean, well, depends on what you do, right? Like what you specialize. But when you become a math major, let's just put it that way instead. The big focus is to prove statements, right? Well, what is a statement to begin with? let me tell you what mathematicians count as a statement. Okay, so a statement. Alright, so I'm defining what a statement is. It's a sentence that can be categorized as either true or false. Alright, it's a sentence that can be categorized as true or false. Okay, kind of interesting. So, like I said, right, mathematicians, they call a statement true if it's true 100% of the time, more or less, right? But okay, it says that, so yeah, again, if a statement fails to be true once, then it's a false statement, right? Interestingly enough, you might think that this definition kind of points something out. The possibility of a sentence not being able to be categorized as either true or false, right? Like, you know, do all sentences have to be true or false? That's the question, I suppose. So only the sentences that can be categorized as true or false are counts as statements in mathematics. Again, I guess the one thing to notice, right? I keep saying categorize. A reason why that word is being used is because there are statements that we feel like they probably have some type of explanation. Okay, we have this thing called conjectures, right? A conjecture is a statement that no one has proven to be either true or false. So a big one is called the Goldbach conjecture, which states that every single positive even integer, so every even natural number, is always the summation of either two primes or a prime and one. It's like 2 is 1 plus 1, okay, or 4 is 3 plus 1, 6 could be 3 plus 3, but also 5 plus 1, so on and so forth, right? So that statement, that conjecture, is I think it has maybe about 200 years old, and no mathematician has ever been able to prove that statement. Although, right, the sentence itself, you can probably, yes, it's a pretty good bet that the statement is either true or false. The funny thing about mathematicians is that, if it was false, all you need is a counterexample, right? Well, after all these years, and now that we have computers, even, right, no one has been able to find a counterexample. But just because just because we haven't been able to find a counterexample doesn't necessarily mean that the statement is true. That, I guess, that's one way in which mathematics diverges from all the other sciences. Because by now somebody would have called it, yeah, man, sure, it's true, right? But mathematicians need a proof in order for them to be able to say something is true, right? So again, this Goldbach conjecture is a statement that yeah, I'm pretty sure it's either true or false. However, no one's been able to prove it. So why are we using categorize? Because if I said a statement is a sentence that can be proven as true or false, then that doesn't tell the whole story. We will be leaving basically any statement that we haven't proved out. So again, just a little detour on why we're using the word categorized. There are statements that could be true or could be false. We just haven't been able to prove if they're true or false. Okay, I'll leave it at that. Okay, now I said something about truth tables in the intro, right? Well, suppose that P is a statement. Let's say, I don't know, say that P is a statement, the sky is blue, whatever. Right? So then for every statement, you can always negate it, right? So if P is a statement, if it's really a statement, meaning this statement, the sky is blue, it's either true or false, right? And hey, okay, I don't want to get into some weird things like, okay, it's true sometimes, it's true at specific times of the day, and also assuming that the weather is clear. Under a specific context, yeah, the sky is blue is a statement because it's either true or false, right? Well, for every statement, we have this thing called a negation, meaning the negation of the statement "the sky is blue," for example, we're gonna write we're gonna use the symbol. So if P is the sentence "the sky is blue," the negation of P will be pretty much "the sky is not blue," right? So P is "the sky is blue," and not P, or the negation of P, is "the sky is not blue," right? Okay, what am I getting at is that when you do a truth table, so the statement P can only either be true or false, right? Either the statement P is true or it's false. However, the statement not P, right? Well, if the statement P is true, then the statement not P needs to be false, right? If the sky is blue, if that's a true statement, then the sky is not blue is a false statement. Okay, well, on the other hand, if the statement "the sky is blue" is false, then "the sky is not blue" is now a true statement, right? So basically, anytime we do some type of truth tables, right? Basically, if you have a statement P, then the statement not P will be just flip the values, right? And again, since we just defined that the statement can be true or false, then yeah, these are the only two possibilities. Okay, well, okay, now suppose that instead of having just one statement, you have two statements, right? Suppose you have a statement P and you have a statement Q. And then suppose that you want to figure out what's the deal with the statement P or Q. Let's do P and Q. So as you can see, I'm going to use the symbol, like a triangle without the base, and this is going to signify AND. Okay. Well, if I have so again, right? If P can only be true or false, and then Q can only be true or false, but now I have two statements, right? And let's say that they're independent. So what are all the possibilities, right? Well, I'm gonna say that there's four, right? Either they're both true, or maybe one of them's true but the other one's false, right? Or okay, if we're looking for all the possibilities, right? Possibility one is that they're both true. Possibility two is that P is true and Q is false. So maybe possibility three is that now P is false, but then Q is true, and then one last possibility is that they're both false, right? These are all possibilities. When you have now two statements P and Q, which are like independent of each other, right? Then now we have four total cases to consider, right? Okay. Well, we're gonna say that the statement P and Q. Well, let's think about it, right? Suppose that someone, I don't know, you're like in the Price is Right or something, and you gotta pick a price, and then they say, oh, out of all these items, you gotta pick something that's blue and also a car, right? So if you pick a blue car, then you can definitely get that, right? They said pick something that's blue and a car. All right. So the statement P and Q is going to be true, right? If P is true and Q is true, P and Q needs to be true, right? Well, basically what's going to happen is that if any of these things, if either P or Q fails to be true, then the statement P and Q should be false, So for example, let's say I grab, alright, so P is an object that is blue, and let's say that Q right now is an object that's a car, right? So suppose I pick an object that is blue, but it's not a car. Maybe it's a blue case that I just know has a lot of money in it, right? Well, if they told me I had to grab something that's blue and a car, and I grab a blue case, right? I can't pick that. I needed to pick something that was blue and a car. So this would be false, right? Now suppose that now Q is true but P is false. So maybe like I saw a yellow Lamborghini, right? And I tried to pick it, but then they told me no, you need to pick something that was blue and a car. So that would also be false. This is probably this ended up being a bad example. It was really good in my head, but anyways, right? And of course, if you pick something that's neither blue nor a car, then the statement P and Q, right? If you pick like, I don't know, a green yacht. I guess I should have said a white one, but whatever, right? Again, they told you you needed to pick something that was blue and a car. Well, all I'm saying is again, that was a big idea. That the statement P and Q is only true when both P and Q are true, and false when at least one of them is false. I should have done or first, but actually no, because there's something about the English language that I want to point out, right? So again, how do we define the statement P or Q? And if you wonder why are we talking about P and Q and then now P or Q? So as you can see now, right, this is going to be the symbol for or. If you notice, right, this was the symbol for and, this was the symbol for or. It's really similar to this symbol right here that was supposed to be the intersection of two sets, right? A intersection B, and then A union B, right? So the only distinction is that right here we're talking about logic. So yeah, this thing means intersection, even though it means all the elements in A and B, and this thing means union, even though it means all the elements in A or B, right? But this really straight up means or, and then this straight up means and. Just a very small, quick distinction, but you see similar shapes, right? Okay, so again, right, all the possibilities is true and true, or true and false, false and true, false and false, right? Okay, now I mean again, that analogy I used was not the best one, but let's just keep going, right? Now they said, imagine again you're in the same game show, and they tell you, okay, now you can pick something that's either blue or a car, right? You can pick something that's either blue or a car. So if you still pick a blue car, yeah, that's actually fine. And this is the only thing that it's not really tricky, but I just wanted to point it out, is that mathematicians, when they use the word or, they use inclusive or. Like if someone tells you, oh, you can have if you were a kid and someone told you, oh, you can either have $1 or a cookie. Well, if that kid's a math major, he's gonna be like, well, okay, let me get the dollar and the cookie. And any normal person would be like, no, it was one or the other, right? Well, to math majors, when math majors use the word or, they pretty much always mean the inclusive or, meaning picking them both is also an acceptable outcome. I mean, yeah, like I said, taking in this example, right? Someone told you to pick a something that's either blue or a car. So if you pick a blue car, yeah, I mean, they're not gonna get mad at you, right? Well, anyways, that's just a math major distinction about the word or. Okay. That being said, again, if you did pick the blue case with a lot of money, whatever color it was, even though it was not blue, again, P or Q is still true. Or if you pick the yellow Lamborghini, again, P or Q still true. But if you pick neither, right, like I said, like it was a green boat or a white boat, whatever, that's the only time where it will be false. So yeah, the statements, the negation of a statement and an or are really important in mathematics. But I guess not as important as this one, right? The one that basically kind of all of math is built up on. So suppose you have statement P and Q. What do we say about the statement if P then Q? Right? So for example, if I tell you if you add two even numbers, you will get an even number, right? So the P is add two even numbers, and then the statement Q is going to be their sum is even. Okay, so again, what are all the possibilities? True, or true, false, false, true, and false, false, right? So how do we deal with the statement if P then Q? If you add two even numbers, then the sum will be even. Well, okay. I when people talk about the statement if P then Q, they usually like to talk about politicians. I like if a politician promises, like if they say, if you elect me, then I'll make this happen, right? Now I will say that I'm filming this video in 2022, and I feel like people really don't like politicians right now. So instead, I'm doing this more mathematical statement, right? So if I tell you, again, I'm telling you right now, if you add two even numbers, then the result, the sum, is going to be even. Okay, well, when, in which situation am I a liar? Suppose that you do add up two even numbers, and then it happens that you do get that their sum was also even. Would you say that I was being truthful, or would you say that I was lying? I think at that point you would say I was truthful, right? I told you add two even numbers, you get an even number. That's what you did, and that's what happened. Then, yeah, I will be telling the truth at that point, right? But then suppose that you do add two even numbers, but then for some reason, when you add them, you somehow got an odd number, Well, at that point I would be lying, right? Assuming that we agree that a number can't be both odd and even. So in this situation, I would be lying. But what happens in the other two, right? Well, suppose that you didn't add two even numbers, but then somehow somehow your sum ended up being even, right? Or suppose that you didn't add two even numbers, and then you didn't get an even number, right? What I'm trying to say is that in both situations, am I guilty of anything? Like I said, I told you, basically any if P then Q statement is a promise I'm making you, right? But you have to make sure that that you make P happen. I'm saying if P happens, then I promise you Q happens. So if P doesn't happen, can you call me a liar? Like I said, if you add 5 plus 3, right? Those are not two even numbers, but 5 plus 3 is 8. So somehow I get the feeling that you might want to say, yeah, oh wow, you were being truthful. I'm saying this, that you need to look at the statement if P then Q as its own statement, right? I said if you add two even numbers. I didn't say anything about you doing something other than that. Like if you deviate from the plan, That's not on me, right? So what I'm trying to say is that actually, because again, you added 3 plus 5, and somehow which again, you didn't do what I said. You didn't add two even numbers, but then somehow you logged out, right? Well, suppose now that you don't, right? Suppose you don't add two even numbers, which means, let's say you add 2 plus 3, right? 2 plus 3 is 5, and 5 is not an even number, right? So false, false. What I'm saying is that you know what, this, that's not on me. I said if P then Q. I said if you add two even numbers, then you will get an even number. I didn't say anything about anything else. So basically I'm saying that these two right here are true, kind of because it's not on me. And if you think, oh well, that's some explanation, this is the agreed upon definition of what is the truth table for a if P then Q statement. If P does happen and Q does happen, then sure, I was telling the truth. But if P happens but Q did not happen, then I was being a liar. However, if you didn't do what I said to begin with, why do you expect Q to be anything, whether it's true or false, So again, my statement is if you add two even numbers, their sum is even, right? If you don't add two even numbers, why would you say that my statement if P then Q is false? So again, I wanna make a video that's actually bite-sized and for people to actually enjoy. So I think I'll end it there because I think that's a good place to end it. Make you think. But I promise you for sure, this is the established truth value, or whatever you want to call it, of the statement if P then Q. The statement if P and Q is going to be true if they're both true, false if it's true and false, but then true if P is just false to begin with, meaning Q doesn't even matter at that point. So true, false, true, true. This is how people that deal with logic see the statement if P then Q. All right. So again, I'll leave it this short, and we'll continue on the next one. All right. If there was something that I didn't make clear, something you want to talk about, maybe you can come up with a better explanation for the and the or. I mean, not explanation, but better analogies or comparisons, right? But I mean, I guess I should say yeah. So this is the P and Q. This is the established agreed upon values for the P and Q statement, and P or Q. All right. Again, I don't want to make this too long. So see you in the next one.